Today we will continue considering the
Recording in progress.
maximum principle. I'm going to prove the following proposition. Two. Suppose that the following coefficients are given: AJSX, BIJSX, CSX. They are given for all I and J from 1 to G, and they are given for all S, X, such that S belongs to 0, T, and X belongs to RD. Okay, and we suppose that these functions are continuous, and our standard assumption that the matrix with these entries is non-negative definite, rho theta, and S and X, and we suppose that CSX takes on non-positive values. Now, if we have a continuous function, let U S X be a continuous function such that the limit inferior as x goes to plus infinity, norm x goes to plus infinity, U S X is non-negative, uniformly in S. Then the inequality U T X is non-negative for all X from RD implies, this inequality implies the following one, the following. USX is non-negative for all S 0T and X from RG. So you see, if I forgot one more condition, such that limit and and L U S X is non-positive for all S X, for all S from this interval and X belongs to RD. So we have in the previous proposition we had a function in a cylinder, okay? And now we have a function in the whole space, dt, okay? And if this function is continuous and satisfies this inequality, and additionally this condition on the infinity, this is a condition on its behavior on the infinity, yes? And X goes to infinity. Then, if you know that it takes on only non-negative value on the right end of the time interval, yes, then it must take on only non-negative value at any point in dt. L is our operator associated with these coefficients. Okay, let us prove this proposition. Let epsilon be an arbitrary positive number. Consider the function v s x that is equal to u s x plus epsilon. I am going to prove that VSX takes on only non-negative values. Okay. So let S0 x0 be a fixed point. So S0 is a point from 0 to t, and x0 is an arbitrary point in Rd. I am going to prove that Vs0 x0 is non-negative. So, using this property, for this epsilon, there exists such R, that Usx is not less than minus epsilon for all x that are in the complement to this ball. And this inequality is valid for all s, because we have here uniformly in s, okay? So there exists, for this epsilon, there exists such R that Usx is not less than minus epsilon for all x if S0 x0 belongs to this ball. It's okay. If not, we can take somewhat greater R in such a way that x0 belongs to ball, to this ball. Okay, and now we have a continuous function in the cylinder 0t Vr of 0, and we know that the function Vsx takes on non-negative values on the lateral surface of this cylinder, and it takes on non-negative values at the front lid of this cylinder. According to proposition 1, we can assert that Vsx takes on non-negative values for all Sx from this cylinder. Okay, and therefore Vs0 x0 is non-negative, and it is what we we are going to prove. So this is a very simple assertion. And now let us consider some auxiliary function. You may notice that in all the arguments, like the maximum principle, the auxiliary function plays a very important role. I denote it by h of Sx, and we choose this as follows. This is exponent to the power k norm x squared t minus nu t minus s plus nu t minus s. We consider some fixed t so s is a point from that interval. K, nu, and nu are positive constants. Now we will suppose that coefficients of our differential operator are given as in the previous proposition, and we allow them. We suppose that they satisfy the following condition. The entities of the diffusion matrix are bounded functions. The coordinates of the drift vector may increase as x goes to plus infinity. If Aj is bounded at these conditions, of course. is valid, and CSX without absolute value x squared. These inequalities are supposed for all ij from 1 to d. Yeah?
Was C negative?
No. Now, if C negative,
So now we assume that C, so C may be positive now, but not
but not
not too much.
Not too much. Yes. Okay. And now I define the operator L as usual. It includes derivative with respect to S, derivatives with respect to xj, derivatives of the first order with respect to xj and the corresponding sum, and the second derivatives with respect to x, jxi, and csx multiplied by u. Okay, and now we prove the following proposition. Three. For any k, there exists constants mu positive and mu positive such that LHSX is non-positive for all S from the interval 1 minus 1 over 2 mu t and x from RT. So our next reasoning will concern some small interval, maybe not so small, but it is important that for any k, I can choose mu and mu in such a way that L, this operator, applied to H, that function, H, S, X, the result is non-negative, non-positive values. Okay, and this is true in some layer. This is a layer, yes.
I'm
It's
sorry? So, can this interval be empty?
no. Why? Why?
Well, if
Oh, it may be small. It may be small, but fixed. Its length is fixed. Fixed. So we have some for variables s and x. We have some layer. Yes, s is in this interval and x belongs to Rd. Our main theorem will be proved exactly in this way. We start from a positive value on the right hand side and right hand end from our interval and construct some interval where the positive where the values are positive, and the next step is the same reason for the next interval and so on. And now let us prove this proposition. So we have to calculate that value. Let us calculate LHSX over HSX. So I need H prime of with respect to Sx over Hsx. It is equal to minus nu and S minus mu k norm x square over t minus mu t minus s square H prime xj Sx over Hsx is equal to kxj over t minus mu t minus s. Okay? And H second prime xj xi of Sx equals two k symbol Kronecker's symbol I J over T divided by HSX. I'm sorry. Uh, 2K Kronecker symbol over T minus mu T minus S and plus 4K square X J X I T minus mu T minus S square. Okay, we have derivative with respect to S, derivative with respect to xj, and second derivative, the second derivative with respect to xi and xj. And now we have to substitute all that in our operator. And we have L H S X over H S X equals minus mu and minus mu K norm X square over T minus mu T minus S square. Okay, now 2K plus 2K over T minus mu T minus S, the sum over OJ from 1 to D, AJSX, XJ, okay, plus 2K over T minus mu T minus S, the sum over OJ from 1 to D, VJJSX plus this term, so we have 4K squared over T minus mu T minus S square, the sum over all I and J from 1 to D, BAJS plus CSX. I divided by H. So, and now let us use our assumption about the coefficients of our operator. So I am going to obtain here something times norm x squared plus some constant. I'm going to receive this estimation of this kind. So let us consider that terms here that will be estimated by something times norm x squared, CSX, and here we have also that term. So this one, how to estimate? Maybe I'd like to write here. Bijsx less than m in absolute value. So this sum is not greater than m. The sum ij from 1 to d, absolute value xi, absolute value xj. This is m, the sum xi from 1 to d squared. And this is, according to Cauchy inequality, is less than d m d norm x squared. Okay? Maybe let us write down x squared multiplied the first minus mu k t minus mu t minus s squared. Okay? Plus plus 4k squared m d over t minus mu t minus s squared. CSX gives us m norm x square, yes, m times norm square norm of x, and let us consider this sum. AJSX XJ is less than M1 plus norm X. This is estimation for this factor, okay? And the norm, the sum over all j from 1 to d, absolute value of xj, so this is less than or equal norm x square root of d. Okay? And you see, we have here such a function 1 plus xi for positive xi, negative, non-negative. Okay? Xi plus xi. 1 plus xi. This is the graph of this function. This is -1, -1/2. But we are interested in for positive xi. Okay, so how to estimate this? This expression for positive xi. It is not difficult to see that it is less than 2xi squared plus 1. Is 2xi squared plus 1, 2xi squared plus 1 is higher. This graph is higher than this. So we have here the following situation. The sum is not greater than m square root of d 2 norm x squared plus 1. So I now write down all that contains norm x squared. So I would like to write down here m2 m square root of d. Okay? So there is no more x squared. Okay. And now we write down all that remains. Minus nu. Okay. From this sum we have 1 m square root plus 2k 2k m square root of g over t minus mu t minus s. This sum is less than dm, d times m, 2k m d over t minus mu t minus s. Okay, and here we have m plus m. So this is our estimation. LH of Sx over HSx is less than or equal to this expression. Okay, and now let us notice that if S is from the interval 1 minus 1 over 2 mu t, then this expression t minus mu t minus s is not less than 1/2 t, and not greater than t. It is a very simple calculation. Okay, so we now this expression in the denominator, if here is plus, we will replace it by 1/2 t. Okay, and if it is with minus, so I replace it but by t. So I will obtain some expression that allow us to make some conclusion. Okay, but now let us make some break. Okay, so we can
Recording in progress.
continue these inequalities. So x squared with sign minus, we put here t, okay, minus mu k t squared plus t over 2. Here we put here t over 2 square, yes? So we have 16 k square m d over 2 square. plus n plus 2m square root of g plus minus nu plus 2km square root of d t 4k over t plus plus 4k m d over t plus m. And now you see that if k is given, if some positive k is given, we can choose the numbers mu and nu in such a way that this multiplicator is negative and this item is negative. So in this, for this s and all x, and all x from RD, we have the following property of our auxiliary function. For any k, or any positive k, there exists a number mu positive and there exists a number nu positive, such that LH over H Sx is non-positive in this layer. So the proposition 3 has been proved. And now let us formulate the main theorem. Theorem. We suppose that the coefficients A, J, S, X, B, I, J, S, X, and C, S, X are given for all I and J from 1 to D, and they are given for all S, X from T are D, and we suppose that these functions are continuous. And satisfy the condition of the conditions of the previous proposition. That is, Bij of S x absolute value is not greater than M, AJSX absolute value not greater than M1 plus norm X, and CSX is less than M1 plus norm X squared. Okay? And now let a continuous function USX be given such that LUSX is non-positive for all S and X. X from RD. Okay. And suppose that, so this is a continuous function for which LUSX is non-positive at every point for that set. And suppose that USX is greater than minus B X beta norm square norm of X. This is true for all S from 0 T and X from RD. Then the inequality UTX is non-negative valid for all X. This inequality implies the following one. USX is non-negative for all S and OX. This is the main theorem, and the the uniqueness theorem for the Cauchy problem for our differential equation is a very simple consequence of this theorem. So this is the main theorem in this in this topic that is called the maximum principle.
B and beta are some positive constants, right?
Yes. Oh, I forgot to say B, and beta. Some given USX is estimated from below by this function. Okay, so we will consider the proof. We will consider the function Vs x that is defined by this equality U S x over H S x. And I am going to show that we can apply proposition 2 to this function. Proposition 2, but not in this region. S will be a point from 1 minus 1 over 2 mil T and X from RD. I'm going to apply proposition 2 on this interval. I know something about this function H that so we need some estimation. U VSX is greater than minus B X norm X square beta minus K over 2 over T minus mu T minus S okay. This H was defined by this exponent. Okay, and now I should choose K and k in such a way that this factor is negative. Then Vsx as x goes to infinity, the limit inferior of Vsx will be non-negative. Okay?
Excuse me?
Yeah.
We also had mu in the definition of h.
Yes. Oh, yes, nu. Thank you. E to the power minus nu t minus s. Thank you. I'm sorry. So, how to estimate this? We know that if s is in this interval, so this denominator d mu t minus s is greater than 1/2 t and is less than t. So if here we have minus and here minus, okay? How to choose k? No, how to estimate here denominator? If I put here 1/2 t instead of this number, I will minus. Okay, this is not less than. This number is less than 1. Oh, e to the power minus nu t, yes? Minus 1. Oh, okay, minus 1 minus b. And here we have x square of the norm x beta minus 2k over t. So if k is greater than beta t over 2, then we choose. Now we choose some k greater than beta t over t. Okay?
I'm not sure about 1/2 t. Maybe we should take t
Maybe
because
here is minus and here is minus. Yes? Let us think. If I put here t,
so this is less, then the fraction is bigger, then with minus it's less, then exponent is less, then exponent with minus is bigger. So we should take t.
what about this minus? We have it is not so important, but it is not difficult to comprehend that we can choose k such that this that the estimate will be of the following form: VSX minus Bx minus something lambda okay, and this means that the limit inferior as x goes to plus infinity, Vsx is non-negative. Okay, and in order to apply proposition 2, we have to calculate L V S X. This is not very simple task, but I would like to show that L hat VSX is non-negative for all S 1 minus 1 over 2, T and X from RD, where L hat has the same coefficient Bij of Sx and its coefficient Aj of Sx are given by Aj Sx plus the sum over all L from 1 to D Bjl Sx H prime over XL with respect to XL Sx over H Sx and C capital C hat Sx is LH Sx over H Sx. So this is negative in this layer. And this is a calculation, and that calculation gives us the following result. L capital VSX equals LUSX over HSX. LU is non-positive in accordance with our assumption. Okay? H is non-negative function. This calculation, I recommend, I advise you to calculate once for yourself, and you verify that this is true. It is not so simple task because you remember that VSX is USX over HSX, and it is very good observation of the author of this theorem that VSX satisfies this equality with this operator L in this layer. This is non-positive. So we have some function VSX as in proposition 2 that satisfies the inequality L hat V is non-positive, and the limit inferior as x goes to infinity, Sx is non-negative. Uniformly with respect to S, we saw. So, this completes the proof. We apply the proposition 2, and we may assert that the function Vsx is non-negative in this layer. The next step, we consider the next layer. Minus 1 over 2 m squared t, 1 minus 1 over 2 m t, and v and x. So we can assert that our function is non-negative in this, and so on. So the fact that UTX takes on positive values for t capital implies that USX takes on only positive, only non-negative values in all this layer. And as a consequence of this, so this calculation, there is no other way than take derivatives and calculate. And it is not so bad, because you see, you can write down some parabolic operator applied to V, and this is non-positive, so we apply theorem proposition 2. Okay, now the theorem of uniqueness of a solution to the Cauchy problem. So, suppose that the coefficients are the same as in the previous. Theorem. And we consider the following Cauchy problem. L U S X equals F S X for S and X from RD, and initial in the sense of final value is a given function f as x, and phi x is a given function. The assertion is there is no more than one solution to this Cauchy problem. Satisfying the inequality USX in absolute value is not greater than B X beta X squared.
What about phi?
I am not speaking now about the existence of the solution. I
So for any phi, there is no more than one.
no more. Yeah.
Absolute value of u
Be,
is
because if you have two solutions, we consider the difference, and that difference satisfies this equation with 0 here and 0 here. So this is a very simple consequence from this. Why? Because you see, if you consider the function usx, maybe let us a few words. Let us consider difference between two solutions. So u is the difference. So we have here 0 and here 0. So consider usx, the function usx. It is greater than minus b x beta x squared, and L u s x is equal 0, so it satisfies this inequality. So it must take only positive, only non-negative values in this layer. And now consider the function minus usx. It satisfies the same inequality. Okay, the same. Minus b x beta square, and it minus usx satisfies the same. It satisfies this equality, so the same inequality. So it minus usx must take only non-negative values, and this means that usx is equal to 0 identical. So this is a very good theorem. We will use it, and it means that there is only one. If there is, then no more than one solution satisfying this equation, this inequality. And what about, it turns out if a function does not satisfy that equality, but satisfies this one, constanta x beta square 2 plus epsilon. 2 plus epsilon. And there is there is a solution other than 0 for this Cauchy problem. So this is very, so we have some uniqueness in some class of solutions. Okay? That's all for today. See you next